Okay, so we're going to work out number 10 from our rotational energy homework problem set. And there's a lot going on there. Basically, there's three different steps to solving this problem. You ultimately want to find your rotational kinetic energy value for the front wheel of a bike. Okay, but before we can go there, to find rotational kinetic energy, we need to have the moment of inertia for the bike wheel, and we need to also know the angular velocity of that wheel. Okay, so how do we find those things? The only thing that we're given is the velocity of the bike, straight line, straight down the street velocity of the bike is 8 meters per second. Okay, we know the mass of that front wheel is 1.6 kilograms. We know the radius of the wheel to the outside edge of the wheel is 0.33 meters, and we know that the wheel is zero point 0.1 meters thick. So, in other words, just basically the this thickness right here, right? That right there is zero point 0.1 meters, all right, or 10 centimeters. So that's what we know. How in the heck do we solve this problem? Well, first off, let me suggest that we find our omega. Okay, we want to find our angular velocity of the wheel to begin with. Okay, so we need to find our omega for a wheel, but what we have right now is actually, so for this circle right here, redraw this a little better. What we have is a velocity going this way, okay? We're going down the street at 8 meters per second, okay? But think about a bike wheel. A bike wheel doesn't slide down the street, right? It doesn't do this down the street. When it's going down the street, right, and it touches the ground the whole way, it rolls the entire time. So it's constantly making contact with the outside of the thing, and it is constantly rolling without slipping, okay? At least in most cases. You don't want to be slipping on that, I guess. So in most cases, you're going to get a roll action out of your wheel. So even though the center of this thing is going 8 meters per second, every part of this thing also has to be going 8 meters per second, right? Center of that is 8 meters per second straight line velocity, so is the outside part. All of it is traveling at that speed. So if that's the case, we can figure out how fast we're going rotationally around with this thing, okay? What we need is this right here. This formula will take, given our radius of the wheel, and the velocity, the straight line velocity, will actually give us an angular velocity for that wheel. So if this is 8, right, we plug in here. So we'll get 8 for our V, okay? Omega, we don't know, we want to find it. And our radius to the outside of the wheel, the part that's making contact with the ground, is 0.33 meters. Sorry, rewrite that so it's easier to see on the screen. 0.33 meters. So now we can rearrange to solve for our omega. So divide this by 0.33, both sides, right? That goes away. And you're left with your omega. And your omega now is going to be third. Sorry, I guess I need to pull this up. Okay, so 8 divided by 0.33. You're going to get an omega of about 24.24 repeating, 24.24 radians per second. Okay, so that's your omega. Now we've got that. Okay, so that's good. So we've got one of our terms that we need for rotational kinetic energy. What we also need to do is find our I, though. We still don't have that. We don't have our moment of inertia for this wheel. So how do we find that? Well, we got to go to our I value, and you look it up for a hollow disc, okay? For a hollow disc or a hollow cylinder, same thing. You actually have an interesting thing happening. If it is entirely a shell, you actually get one kind of I value, but if it is like a ring, you get this formula right here that you have to plug in. This allows for various thicknesses of the wheel. Okay, so what does this mean? A squared, B squared. A is your inside radius, okay? B is your outside radius. So let's go ahead and do this for the wheel. I of the wheel is going to be 1/2. We know that's not going to change. The mass of the wheel, we know, it's 1.6 kilograms. Okay, times, now our inside diameter we'll find out in a second. Our outside diameter we already know. The radius to the outside, sorry, I keep saying outside diameter. I mean outside radius. These are radii I'm looking at. Inside radius, outside radius, okay? So B, we already know our outside radius. It's 0.33 meters. 0.33. We got to square that, okay? Plus, let's see, hopefully I have enough room for this. We need our inside radius squared. And our inside radius, well, the wheel is 0.1 meters thick. The outside radius is 0.33. So the inside radius has to be 0.23, right? Subtract one from the other. So our inside radius is 0.23 meters, and we got to square that for our formula, okay? So now we can find the eye of our wheel. So let me go ahead and find that. Okay, so here we go. I got 0.5 times 1.6 times, and the parentheses around all this fun stuff. Sorry, if I hit parentheses twice on here, it changes it to a bracket. It's kind of pain. All right, so the eye for the wheel is, make sure I got my math right. Okay, it is 0.1, basically 3. It's 12944. Okay, but I'm gonna call it 0.13 because why? Why go there? Do not make it more painful than it needs to be, right? So there is our moment of inertia for the wheel. Okay, so we found two things for this problem, right? So far we found our omega, and now we found our I. And look at this, I and omega is all we really needed to find the rotational kinetic energy. So now I can plug this in. So let's do that. So rotational kinetic energy, that does not look like a K, it looks like the beginnings of an E. There we go. Rotational kinetic energy is 1/2 times I times our omega squared. Okay, so that is 1/2 times our I was 0.13, and our omega was 24.24, but remember our omega has to be squared. So if we solve this out here, then we'll find our rotational kinetic energy. So let's go ahead and do that, all right? So I will do 0.5 times 0.13 times 24.24 squared. And what I get is I get 38.19 with some other stuff added on top, but we'll just end it there. 1925. So 38.19 joules is our rotational kinetic energy for that front wheel. That's it. All right. So remember, steps here. You have to get things into terms of rotational terms, right? An omega instead of a v. Easily done. Remember, anytime you want to get to a straight line version from a rotational version, you multiply it by the r. If you want to go the other way around, if you want to get to the rotational version, you have to divide your straight line by your r. If you remember it one way or the other, you'll be good to go, because then you can just rearrange the formulas you needed, okay? So that's how we get to our omega. To find our I, we have to look it up off of a table. It has to be given to us somewhere. I'm not going to expect you guys to memorize this, and neither will they on the AP. They will give you these values. They might have you calculate it out based on some stuff, but that's about it. So here we've got the formula for a wheel. It's not given to us because it changes based on the inside and the outside radius. Radiuses, radii, right? Okay, so there's, again, once we plug all that in, you get the I for the wheel. Use that and that, your rotational terms, to find your rotational kinetic energy, and voila,